N. Very good. Let's embiggen. Rule page off. Okay, so drag force. All right, you guys. So drag force is what last year what we called air resistance. Okay, so we're going to use the symbol FD. Okay, I believe your textbook just uses the symbol capital letter D. Okay, but what you need to know is drag is a force. All right, and so the idea is as you move through the air or any fluid, whether it's a liquid or a gas, as you move through the fluid, you have to push molecules of that fluid out of your way, right? And since you're pushing the molecules are pushing you, right? Third law. And so it resists your motion. Okay? And it also turns out, and this is another thing we learned last year, that the faster you go, the larger this force is, right? Which should make some kind of conceptual sense, right? Because the faster you go, the more molecules you're going to have to move per second, right? Because you're just going to encounter more of those particles. And you can feel it. Like if you move your hand, you don't feel anything, right? But now do it fast. Oh, you can feel it, right? Okay? So when you do this, you can feel your hand pushing the air. But if you do it slowly, you don't really notice it, right? Good? Yeah, all right, so. All right, you guys. So last year what we learned was that if you drop an object, it will eventually reach what's called terminal velocity. Okay? And the reason for that was because as the object moves faster and faster, your force of air resistance, your drag force, gets bigger and bigger. Okay? So let's suppose we've got, I don't know, whatever, a 2 kilogram object. All right? So if I drop a 2 kilogram object, then what's going to happen is when I first release it, it's at rest. So the only force on it would be gravity. So negative 19.6 newtons, right? If there's no air resistance, that's going to make my acceleration negative 9.8 meters a second squared, because my net force would just be negative 19.6 newtons, right? Follow? But because it's accelerating, it's going to start moving faster, right? And as it moves faster, it begins to have to push more air, right? So maybe a moment later, maybe now the force of gravity is, well, still 19.6, right? But now maybe we've got, I don't know, 5 newtons of air resistance. Follow? So that's going to decrease our net force. So now my net force, instead of being negative 19.6, it's only negative 14.6 kilograms, right? Oh, newtons, sorry, that's embarrassing. Newtons. And so then the acceleration is, what, 7.3? Negative 7.3 meters a second squared. All right, now, does this mean that it's falling slower? No, it means it's accelerating slower, right? It is still gaining downward speed, right? My acceleration is still a negative number. So my velocity is going to continue to get more negative, but just at a slower rate. Does that make sense? So it's like, at the beginning, we've got the gas pedal all the way down to the floor. Here, we're going to gradually let up on the gas pedal. So we're still gaining speed, but just not as quickly as we were when we had it all the way down to the floor, right? Okay? So as time goes on, this process repeats itself. So I'm going to move into this space down here because I don't think I need it for anything else. So a moment later, my force of gravity is bigger, negative 19.6 newtons, but now my drag force is bigger. So maybe the drag force now is, I don't know, maybe it's 15 newtons. Right? And so now my net force is only, what, 4.6, negative 4.6 newtons? And so now the acceleration is negative 2.3, right? So anyway, we could keep doing this indefinitely, but so eventually what's going to happen?
Net force is 0.
Oh, sorry, Margaret, what do you got?
Is that 15 newtons?
Yes, 15 newtons, sorry. That's okay, my handwriting's not very good. Peter?
Force of gravity will equal the force of gravity.
Oh, right, yeah. Okay, so Margaret, were you good?
Yeah, I'm sorry. I just.
Oh.
Oh no, sorry. So sometimes when you're writing, because you're writing.
I know, because I stand in front of it, yeah. Okay, so Peter, you are exactly right. So what's going to happen is, as it moves faster and faster, this drag force here gets bigger and bigger. And as it gets bigger and bigger, it's going to get closer to being positive 19.6, right? Okay, and so when that happens, now my drawing looks like this. Gravity's still going to be pulling down with negative 19.6 newtons, but my drag force could, theoretically, achieve that same value. And at that point, what's my net force now, you guys? 0, which means my acceleration is 0. Does that mean it stops moving? No. It just means it stops accelerating, right? Follow? All right, the velocity at which this occurs, the velocity at which your drag force equals your gravity is called terminal velocity. Good? All right, now, somebody last hour said, does that mean it's hit the ground? No. Or in my honors class, because we were talking about this in my honors class too. No, it's still falling, but it's falling so fast that the air resistance is canceling out the effects of gravity. Follow? All right, any questions with that? Yeah, sorry if I'm going too fast. Sorry? Yeah. All right. Everybody caught up? Carly, you good? You still need a minute? All right, so I think I can say this while people are writing. So this last little blip here, I think we talked about this yesterday. All right, so last year when we did honors, this was pretty much as far as we ever got with drag force and terminal velocity, right? It was either I would give you the drag force and you'd find the acceleration, or I'd give you the acceleration and you'd find the drag force, right? But what we never were able to do was figure out what...
Interruption. This is the final call, final last call for Life Touch Retake.
Said that last time.
Final,
Okay, speedy quick, Evan. Okay. Oh, you're just throwing your apple.
Again, this is the
Throw your apple faster.
Life Touch Retake pictures. They will remain here in the auditorium until 11 a.m. At that time, if a student has missed, to send them to the main office. Thank you very much.
Okay, shoot, that announcement came at a okay, so again, so last year, the only two values we ever looked at were the force and the acceleration. But we weren't ever able to calculate the velocity, right? Because everything we did last year was a problem where the acceleration was constant, right? And we learned that if your acceleration is changing, the only way that you can find velocity or displacement is to use calculus, right? And that's exactly what's going to happen here, right? Because as my net force changes, so does my acceleration, right? Follow? So how do we deal with that? So it seems like, oh, well, we just take an integral, right? Because the integral of acceleration is velocity. But it's not that simple because the force depends on the velocity, not on the time. Okay? And so that's where the difficulty lies. All right? So we'll get to that math in a minute. Honestly, so here's the deal. Last year I spent all this time teaching this. This is how drag force is presented in the book. Okay? So it turns out there's this equation you can use to calculate drag force. All right? And it's this mess. So it's 1/2 times c. So c is kind of like, you know when we do friction, there's a coefficient of friction?
Yeah.
All right? C is a coefficient of drag force. Okay? It's determined by the shape of the object, the surface area, sort of how the thing is configured. All right, it depends on the density, so this little Greek letter rho is the density of the fluid that the object is moving through. Okay, so why would the density of the fluid matter?
So there'll be more particles you have to push out.
Good, there's more particles. If I drop a bowling ball off the Empire State Building, it's going to take a long time before it hits terminal velocity, right? But if I drop a bowling ball off of a boat, as it falls through the water, because the water's denser, it's going to hit terminal velocity faster, right? Does that make sense? Okay, so it depends on the density of the fluid, depends on the surface area of the object, cross-sectional area, and then it depends on the velocity. Okay? So, this is an equation. I have never once seen this equation on the AP test, so don't worry about it. Okay? So this is just kind of like some background stuff, okay? All right? So the way that the problems on the AP test are usually formatted is this. The idea is, in a given example, all of this garbage is going to be constant, right? Right? The coefficient of drag force, or the, what's it called? The drag coefficient, thank you. The drag coefficient isn't going to change because the shape of your object is going to be constant, right? Density of the fluid it's falling through is going to be more or less constant. Surface area is going to be more or less constant. So really, it boils down to your drag force is equal to some constant k times v squared. Follow? All right, and then sometimes they simplify it further, and they just, I honestly don't know why they do this, and I need to find some time to do a little bit more research and see when this would be a thing. But sometimes they say, suppose the drag force is this, some constant times v instead of v squared. Okay? So in both cases, the drag force depends on the velocity. In this instance, it just sort of depends on the velocity more, if that makes sense. Okay? So I don't know if maybe in different fluids, maybe the drag force is closer to this pattern. Regardless, all of this is not really a law. This is in sort of an experimental equation. Okay? Like last year we learned about, I'm not ignoring it, I just want to finish my train of thought. Last year we learned that you can find coefficients of friction, right? But where do those coefficients of friction come from? Normal force and the force needed to drag it, right? So, but they're experimentally determined, you know? Like there's a book somewhere at MIT that's just got, you know, whatever, ice on iron, ice on wood, ice on different temperatures and stuff, right? And it's got these coefficients of friction. But they're all experimentally determined, you know? So same thing is true here. These are just sort of based on observation. This is the pattern that drag force follows. And so apparently there are circumstances under which it's just k times v instead of k times v squared. All right? Peter, you started to ask something.
Yeah, I mean, I was just getting a little, like, wouldn't that radically change the force?
100%. Yeah, that's what I'm saying. And I honestly need to do some research and figure out why the AP board does this on some of the problems. My guess is they're just simplifying it. They'll tell you. They'll tell you which one to use. So the way the problems will be worded is it'll say, suppose the drag force is, and then it'll basically give you one of these two options. Okay? And then you just need to use it. Follow?
Yes.
Okay. So,
K is infinitely variable, so.
sorry?
K is infinitely variable, right? So it kind of makes sense.
Well, a little bit, but the problem is this equation says if you double your velocity, you quadruple your force. This equation says if you double your velocity, you double your force. So they do contradict each other. Peter's exactly right. This sort of is like, what the bleep? Like, where did this come from? Okay, so anyway, I think in terms of like, if you're just trying to prepare for the test, I think it's not an issue. Just sort of like, you know, accept it at face value and solve the problem based on the equation they give you. Okay? So, all right, so here's an example. This is not an exact problem off of an old AP test, but it's very closely modeled after the way that the AP problems are worded. Okay? So, it says, for example, an astronaut in a space station throws an apple of mass m to another astronaut. He releases the apple with a speed of v naught. If the only force on the apple is the air resistance, and then it gives you this force, and they used b instead of k, does that change anything? No. Okay. Where b is a positive constant, then we've got some stuff to solve. Okay? So, why is there air resistance in space? Because they're in the space station, and they have air in the space station.
Oh, yeah.
Cool?
Right.
All right. So,
Wait, would there ever be like a trick question where they're like, calculate the air resistance in space, and they're like, okay, there is not.
I mean, okay, that might be a multiple choice thing, but not a FRQ. Okay, so this is a simple example because, so I'm starting with sort of the easiest possible example. In this example, the only force on it is air resistance. We don't need to worry about gravity. And I gave you the simpler model for drag force, right? We don't need to worry about the v squared. Cool? All right, so to solve these problems, so number one says write, but do not solve a differential equation. Some of you don't know what that is. Hang tight for a minute, and you'll be okay. Solve a differential equation which could be solved to find the velocity of the apple as a function of time in terms of m, the mass of the apple, b, this positive constant, and physical constants. What do I mean by physical constants? What might be, it's not going to matter in this problem, but in general, gravity, g. Okay? Be careful, this is nitpicky when you say gravity. It's not gravity, it's acceleration of gravity. Okay? I don't need to be a pain in the can about it, but it's an important distinction, and I want to make sure you guys understand that g is the acceleration of gravity, not the force of gravity. All right? Okay, so let's draw this. So here's our apple. Look how happy he is. Okay, so which way, sorry, I did it again. Which way do you want the apple to be moving? To the right. Cool. So v, there's the velocity that he threw it at. All right. Now, after he lets go of it, there's going to be a drag force on it, right? Fd equals, well, for us, it's actually negative bv, right? So these are vectors, actually, right? What's the negative telling me? The direction. It's telling me that my drag force acts in the opposite direction of the motion. This will always be true. Okay? Your drag force always acts in the opposite direction of the motion because it's resisting motion, right? Okay? So, we need to somehow come up with an expression for the velocity. So my knee-jerk reaction, and don't write this down please because it's going to be wrong, but my knee-jerk reaction is to go, oh, well, right on. Final velocity is just initial velocity plus acceleration times time. But what's the problem? Why can't I use that? Acceleration's changing. Right? So we're kind of SOL here. All right? So here's how you have to do these. So what I'm going to do is I'm going to write an expression for the acceleration of the thing. In this case, the apple. All right? So let's see. I know that net force in this problem is negative BV, right? And I also know that that is mass times acceleration, right? Okay, so I could, if I wanted to, I could solve this thing for V, and I would get this. V equals, what? Negative MA over B, right? Cool, I solved, I've got a function for velocity. Why does this, what's wrong with it? Like, why am I not done? It's not in terms of time, right? Remember, our big picture goal is to come up with an expression for velocity, not as a function of the acceleration, but as a function of time, right? And the problem is our acceleration is changing as time goes on. So, we need to find, that's exactly right, that's really good. So what we need to do is we need to find a way to put t into this equation. Okay? So what we're going to do is we're going to replace the a with dv dt. So in English, what does dv dt mean? It's the change in velocity per unit time, right? It's the derivative of the velocity, right? Follow? All right, so here's my new equation. V equals negative m over b times dv dt. All right, that's the answer to number one. That's your differential equation. The solving is the part where it's a pain in the neck. So usually, I don't know why they separate it like this. I think they're just trying to give you some guidance when they write the problems like this.
Yes, you know what order.
So that you sort of like, oh, right, I'm going to have to use some crazy calculus to do this. So they give you a hint by saying, hey, you're going to need to write a differential equation. And then the next question says, okay, now that you've got that, now solve it. All right, so this is problem number one. Are there questions on what we've done so far? Okay, so to solve this, we need to find a way, like dv dt, if, right? Okay, yeah.
What happens if there's
Like g, we'll get there. We'll do other problems like that later. Okay, so is everybody okay up to here? All right, so number 2, solve this differential equation to find an expression for the velocity as a function of time in terms of mv and physical constants, which there aren't any in this problem. All right, so you know what, I want to... Ha! Good. I don't know, 500 grams maybe? Okay, so let's solve this thing. All right, so what you want to do is you want to get everything that has a v on one side and everything that, if there was a t in here, which there isn't, but if there was a t, you'd want to get everything that has a v on one side and everything with a t on the other side. All right, so I'm going to rearrange this mess and get it so that all of my v's are on one side and my dv's are on the other side. So I don't like that this is a fraction. So step 1, unfractionify it. So how can I make it so that dt is sort of not in the denominator? Multiply both sides by dt. Okay? Now, so the weird thing is like, I shouldn't get into this. Okay, so anyway, so here we go. So I'm going to multiply both sides of this by dt. So I get v dt equals negative m over b dv. Follow? All right, so now what I want to do is I've got a dv over here. I want to move my v so that it's hanging out with the dv. And if there was a t in here, I would want to move the t over to the dt side. Cool? So I'm just going to divide both sides by v. So now I've got this. dt equals negative m over b times dv over v. All right? Good? Any questions? So far I've used one tiny little calculus concept, right? Just that acceleration is the derivative of velocity. And I've done some algebra. Okay? Carla. Isn't v dt technically change in position? Except that v represents our instantaneous velocity, which is changing. So if you take the limit as your dt goes to 0, that's sort of nonsensical, I guess, you know? Anthony?
Yeah, so you said if there was t on the side, we'd move it over, but didn't we take the derivative?
Yeah, exactly. It's not going to happen. It's going to be a non-issue. That was more just sort of like, here's how you solve differential equations. It won't come up in this class, but just for future reference, if there was. All right, so are we good up to here? All right, so here is the deal. So what I'm going to do now is, the only way to get rid of the dv and the dt is to take an integral. Okay? So this is an oversimplification, but in general, the integral of dx is just x. Okay? The integral of dy is just dy. Okay? Because the d means derivative, and an integral is an antiderivative, so they kind of cancel each other out. All right? That's a little bit of an oversimplification, but that's kind of the gist of what's going on here. Okay? Now, remember, when we integrate, we can either do a definite or an indefinite integral. All right? Our goal is we want to figure out what the velocity is at time t, right? So, here's what I'm going to do. I'm going to take this expression. Let me just write it again so we've got a little bit of room to work with. So we've got negative m over b. That's just a constant, right? So that doesn't affect anything. Times dv over v, right? And I left a little space. If you wrote that down, leave a space because I'm going to put something in there. All right, and on the other side, I've just got a dt, right? Follow? So what I'm going to do is I'm going to integrate both sides. All right? So the left side I'm integrating with respect to t, and on the right side I'm integrating with respect to v. Okay so far?
Yeah.
Now, you could technically put the integral out front, but the integral of a constant times a thing is the same as the constant times the integral of the thing. Did that make any sense?
Yep.
So you can pull the constant out. So I'm going to put an integral here, and I'm going to put an integral here. All right? So my goal is I want to know what the velocity is after time t. So for time, I'm going to integrate between 0 and time t. Okay, so this is going to end up just being t. It's actually t minus 0, which gives you t. Follow or no?
Sure, yeah.
All right. And again, some math teachers would get fussy about this. This is really bad notation to be doing dt and have t as a thing. Nobody in physics cares. Okay? So I care because I'm more mathy, but whatever. We'll deal with it. Okay? All right. Now, over here, during this time, my velocity is changing, right? What was my velocity at time 0?
Initial velocity, V naught.
V naught, right? And at the end of time t, my velocity is v of t, which is what I'm trying to find. Okay? So what we're doing here is we're integrating across equal time intervals. Okay? So in the first t seconds, 0 to t, my velocity is going from v naught to something. And that something is the thing I'm trying to find. Follow? Okay. Now, so this ends up just being t. All right? I will once and only, from this point forward, I'm basically just going to go, okay, that's t. Let me show you why. All right? And I'm only going to do this once, because it won't be an issue. All right? But so the idea is, this is 1 dt, right? So if you're integrating with respect to t, what's the integral of 1? What thing do you take the derivative of to get 1? T, right? So this is just t evaluated between 0 and 1, right? Oh no, 0 and t, sorry. Follow?
Yeah.
So then you're going to get, oh, well that's just t minus 0, which is just t. All right, how are we doing?
Great.
All right, if you're a little confused, the process is going to be the same. So as you try the homework, that first homework problem, you can almost just follow it like a recipe. Okay, the steps are going to be the same every time. Okay, Peter?
Could you re-explain what we did in those last couple steps?
From here to here?
Yeah.
Okay, forget about physics for a second. What's the integral of x squared with respect to x? So that's asking you, what thing has a derivative of x squared? Well, let's see, it's got to be x cubed, right? So when I take the derivative, the power goes down by 1. But that would give me 3x squared, so I got to get rid of the 3. So that's 1/3, right?
Yes.
Cool? All right, what's the integral of x with respect to x? Well, it's got to be something x squared, but it's got to be a half, right? Follow?
Yep.
What's the integral of 1 times dx? Which, incidentally, is the same as this. That's just x, right? Good? So the integral of d something is just the something. Don't use dry erase markers like that. It dries them out. Margaret. No, I was the one that did it. It wasn't even her. See, that's why it was funny. Yes.
I got it.
All right. Is everybody okay with this?
Yes.
All right. So now what we're doing is we're setting our bounds, right? So if I wanted to integrate here between, I don't know, 1 and 4, I would plug in 4, I would plug in 1 and subtract, right?
Oh, okay.
Follow? Or maybe I want to integrate between 2 and some random variable b that we don't know. Then I would plug in b and I would plug in 2 and subtract, right?
Into the thing on the right side. The integral, right?
Yeah, so that would be, so I would do 1 to 4 over here. I would do from 2 to b here.
Got it.
Good?
Yeah.
All right? So, but what we're doing is we want our t to run from 0 to some arbitrary time. So I'm just integrating between, I guess here I use x. Why did I use x instead of t? I don't know. To confuse you, I guess. Sorry. So all of these x's could be t's. All right? So here I'm integrating from 0 to some arbitrary value of t. So, between 0 and t, so I'm going to get t, x is t, minus x is 0. Good?
Yeah.
Did that help?
A lot, actually.
Good. Everybody good? Any questions? Okay, so, oops. All right, so where are we at? Okay, so now we've dealt with the left side of this mess, right? Equals, equals, equals. Now we got to deal with the right side of this. All right, so the question then is, what thing has a derivative of 1 over v? And this is one of the ones, it's a trick, you just got to memorize this.
Natural law.
Okay, so some of you remember it's natural log. All right? Okay, so off to the side, write yourself a little reminder that the derivative with respect to v of 1 over v is the natural log of v, right? Did I do that? Oh, no, backwards, sorry. Thank you, sorry about that. So this is asking me, this mess right in here is asking me what thing has a derivative of, right? What thing has a derivative of 1 over v?
Natural log of v.
And so it's natural log. Good? All right, so when I say these are all going to be the same, almost every time you do one of these drag forces, unless it's kx squared instead of kx, or sorry, kv squared instead of kv, anytime it's kv, it's going to be, you're going to end up having natural log.
This is crazy.
All right, so are we okay or no?
Yes.
All right, so if I who said no? Who did I lose? Okay, all right, if you're lying, I'm around before and after school. All right, so this mess then becomes negative m over b times the natural log of v evaluated between v naught and v of t. Okay, so the negative m over b stays the same. The integral becomes natural log. But then you've got to evaluate it between v naught and v of t. Yep, exactly. All right, so we're not done yet, but is everybody okay so far? What do you got, Adam?
So is that just something we should memorize, that the integral of
dv over v is ln v?
yeah.
Yes. Did you guys all hear that?
No.
That's a thing you should memorize. The integral of dv over v is the natural log of v. Okay? It will come up. It's on your equation sheet, but you don't want to be shuffling through that giant AP board equation sheet trying to figure out what the integral of 1 over v is, right? So I would just memorize it. Any problems? Okay. So, next. So, Carla just said, okay, so what does this mean when we say evaluate it between v naught and v of t? It means find it at v of t and find it at v of naught and subtract, right? So you get negative m over b times the natural log of v of t minus the natural log of v naught. All right, we're getting warmer. We're almost there. But now we got to solve this stupid mess for v of t. We have to. Otherwise, well, I mean, I guess you don't have to, but you would not get full points on the test. So if you don't care, then no, you don't have to. But in my mind, if you're going to sit in my class for the next 5 months, you might as well get a 4 or 5 on this thing, right? So let's do this. All right? All right, so now we got to do 2 things. First of all, we got to find a way to get rid of the ln's, the natural logs. So if you've got a square root, what's the opposite of square root? Squared, right? What's the opposite of sine? Inverse sine, right? What's the opposite of natural log? E to the. Okay? Exponential function, right? E to the something, right? Okay? So, but we're not there yet because we haven't isolated the natural log of v yet. So, there's a couple ways of doing this. What I tend to find works best, as much as it sucks, is to use logarithm rules.
Yeah.
So do you guys remember what's natural log of something minus natural log of something else? Division, right? Is that what you're going to say? Okay. So this becomes negative m over b times the natural log of v of t over v naught. Good? I believe that most of you can get the algebra from here. What should I do?
Can we do it?
Yeah, we're good. Yeah, you want to take a second to do it?
Other numbers.
Oh, we're going to do it. Oh, yeah, I was going to.
Oh, okay.
I just was saying that I think most of you know how to do it from here. All right, so what should I do next?
Divide by negative m.
Yeah, let's move the negative m over b to the other side. So you get negative mt over b. Oh, no, you don't. You totally don't. You totally don't. I always make that mistake, so watch me if I do that. All right, so you get that equals the natural log of vt over v naught. Good? If you're right now going, I hate this, you should also be going, but this is as hard as it will get. Okay? So, if you can do this, you're good. All right, now what? You'll figure it out. You'll figure it out. So now we do e to the. So e to the negative bt over m equals v of t over v naught.
Wait. Slow down. Hang on. Now I'm confused.
Were you good up to here?
Yes, I have that.
Okay, so here's the thing. Forget about physics for a minute. So if I give you y equals the natural log of x,
Yes.
and you want to solve for x,
Either
you raise e to both sides. And it turns out that the function e to the and natural log of are inverses. So these kind of cancel out, and you get e to the y equals x.
All right.
Follow? So I used that exact same trick.
So e to that whole negative bt. Over
Yeah.
All right. That sucks.
It does suck. 100% it sucks. This is taking longer than I thought it was. We're going to have to pick up here tomorrow. Damn it. I mean, darn it. All right, are we good up to here? Okay. All right, so one last step. What should I do? Multiply by v naught. V of t then is going to equal v naught times e to the negative bt over m. That was insane. Holy cow, that is real deal physics. Yes, sir, Patrick. Shh, guys, quiet, I can't hear his question.
What instead of using algebra tools to like combine the two natural logs? You
Yeah, there are other ways of simplifying this.
okay, but it would be a different answer.
As long as your algebra is sound and you've come up with an accurate expression for v of t in terms of t, that was redundant, but yes, then you're good. Here?
So this process would almost entirely change if it was h squared.
Yes, because then but the nice thing is then you don't have to worry about the natural log.
Oh, okay, so that entirely.
Because then you just use the power rule to take the integral.
Nice.
Okay, so, all right. So are there questions here?
Not yet.
Okay, so, whole bunch of math. Whole bunch of math. All right?
Every time I ask
So I tend to see one of these on probably like every 3 years there's one of these on the AP test-ish. Every 3 or 4 years there's one. And it's one FRQ. There was not one on it last year.
Was there one on here the year before?
I don't remember. I will look. All right, but we don't want to gamble. I feel like it's been a little while. If I remember right, the last time was 2013. But don't quote me on that. All right? Okay. You guys, by the end of the year, these are going to be like... The nice thing about these is once you learn how to do them, it's just like, oh, this is one of those. And you just do it. All right? Now... Okay, so that was number 2. Ooh, it is pizza lunch. All right, you know what? We don't have time to do these right now. All right, I'm going to stop there. Cool. know to get